There's some really exciting things about having the ability to proxy to local models through a provider like, for example, Olama, and then Olama could dispatch to DeepSeek R1. Also, to look at the load with this CLI, you could burst out to the cloud. Now, you can directly call Bedrock. That could be one way to do it. Or a more sophisticated way to do this to maybe scale to a global level is to use global scale components. So a good example of this is in the AWS layer here, we could use SQS. Now, what's interesting about a service like SQS is that it has no limits on how much data you can send it. So it's effectively a fire hose with infinite inputs. Now, what could you do with this? Well, we could put a ton of traffic could start pumping into SQS, and then those SQS payloads could, through an event-based mechanism, invoke Lambda. Now, what could Lambda do? Well, Lambda could invoke Bedrock via the Bedrock API in Rust. Also, we could look at CloudWatch to measure the metrics and make sure that we're doing things correctly. And so what we have here is effectively infinitely scalable ability to burst out to the latest models that are foundation models that appear in Amazon Bedrock through the serverless infrastructure, which is a very efficient infrastructure with Rust. And we also have the ability to use local models. And this workflow is really, I think, one of the most cutting edge workflows that people could think about in the year 2025, 2026. And it's also enabled by Rust, which is a cutting edge new systems programming language, and Cargo Lambda, which is a very incredible open source tool that allows you to deploy Lambdas. Now let's talk about some of the technical details here. We have zero cost provider abstraction. We have trait-based dispatch between Olama, Lambda, Bedrock, and this generic over async trait for runtime polymorphism. Also, we have lock-free metrics using the atomic. Some other things you could think about would be Lambda cold start optimization with Tokyo, shared connection pools with Arc Pool, aggressive binary size reduction. Like, could you get it to, let's say, 2 megabytes to really optimize the performance of serverless? Could you do Rust static linking? And then in terms of observability as well, some of the things to think about if you're building a global scale system would be open telemetry integration points, maybe custom CloudWatch dimensions. Dynamo could be for metric retention. And then in terms of production considerations, maybe a graceful degradation to local, right? Because we have the ability to talk to the cloud, but also local, could you actually have that as a kind of a safety mechanism to degrade the performance so that you don't have to actually go all in on one thing or the other. So this is I think a very interesting way to think about some of the next generation services that will be built, and it's worth taking a look. So what we're going to do next is play around with the Rust cargo ecosystem by building a sequential prime generator. Here's a project that shows the power of the AWS ecosystem with Rust and also with an open source tool called Cargo Lambda. If we go ahead and we do Cargo Lambda help, you can see that it taps into the powerful Cargo ecosystem and has a specialized set of commands, including build. This allows you to do Cargo Lambda build, deploy, so you can deploy a function directly to AWS from the CLI. We also have watch, so you can have a development server and interact with it. And then in terms of initializing it, you can also go through here and create a project. You can also do a new Lambda function. You can do system information. There's all kinds of cool things you can do. So let's go ahead and get started here by just doing a cargo format and cargo build. So that's typically what I do when I start working with a project. And you can see that it was able to work. So if we go to main here, we can actually kick through the tires and see exactly what's happening. We have the usage statements here, Lambda runtime. We have deserialization, serialization. We also have a struct here. In this case, this is a prime request. And then in terms of functions here, we have a default start, default count. We also have a prime response, a prime error. So these structs here allow us to specifically have the types that we need, which is one of the benefits of the Rust language. And we also have an implementation here that's a success. And this allows us to deal with the results and also have an error handling. And then in terms of the handler here for the Lambda function, we have async fn main. And this Lambda runtime is going to use the AWS Lambda runtime, which allows us to do serverless invocations. And then there's a handler here that is called by the async handler that does the generate primes. And if we scroll down here, here's the actual logic where we go through here and we do a prime generation. So the reason why I used a prime generation, a sequential prime generation, is just to figure out something that is computationally expensive. And this simulates some of the things that you could do inside of AWS Lambda function in Rust and takes advantage of the efficiency, the energy efficiency, the computational efficiency of Rust. Now, if we go ahead and take a look at a test payload as well, this is something that's kind of fun, is that you can go through here and you can say, oh, look at this. We have a start at 10, and we also want to count 5. So you could say, I want to start with 10, the number, and then I want to do 5 sequential primes. And that's really the starting point for our project. And if we look at cargo toolml here, inside we have all of our dependencies as well. So to get started with playing around with this, what we can do is actually right click inside of this IntelliJ environment. It's going to be similar in different editors, and we can do cargo lambda watch. So cargo lambda watch, and this will actually let this be in development mode locally. So it simulates what would happen inside of the AWS Rust ecosystem. And then from here, all we have to do is invoke it. So we could go to our README here. Okay, now we can see that we already did phase 1 in terminal 1. We have cargo lambda watch, but let's go to terminal 2 here and let's test this payload. So I'm going to copy this cargo lambda invoke. And this is really, in many ways, the killer feature of, in my opinion, cargo lambda, is that there's a binary that runs local, and I can just paste down here and play around with what's happening. And this is awesome because I don't have to do anything tricky to basically do an integration test or do QA on the Lambda that I'm building. You can see it's pretty amazing. And we can also say, okay, we want to start at 100, but now we want to build 100 prime numbers, right? And you can see here that it even tells us the milliseconds required to invoke that. So in a nutshell, the Cargo Lambda ecosystem is a great place to build really high performance global scale solutions. And also it could be a great interface to talking to things like Bedrock, where we can interface with foundation models. So go ahead and give Cargo Lambda a try and consider how you could integrate a system like this with existing foundation models, both hosted on AWS or calling out to potentially a third-party